Welcome back. In this video we're going to talk about line integrals over vector fields. You remember we have already defined line integrals over scalar fields. The idea there was to integrate a function following along a certain path. Now usually if you want to follow a path through a force field where the force changes, then of course the magnitude of the force that you actually feel is also influenced by the direction that you are taking versus the direction of the force. For example, say you're going hiking in the mountains, then you probably have experienced that going up is a lot harder than going down. And that is mainly because going up, you're working against the direction of the gravitational pull of the Earth. While going down, you're going in the same direction, more or less, as the gravitational pull of the Earth. So when you're going up, you have to use a lot more work. You have to invest a lot more energy to work against that force. While going down, the force does the work for you. Similarly, imagine you're steering an airplane through atmospheric winds. Then if you're flying against the direction of the winds, you have to spend a lot more fuel and energy than if you're flying in the direction of the winds. Then you can basically just let the winds do their work and blow your plane forward. We already said that forces and their directions can be expressed through vector fields. So a natural question to ask is, what if we have a path through a vector field? And we want to know how much energy is spent for going along that path under the influence of the force described by the vector field. And that means we have to adapt our idea of line integration to incorporate the force and the direction of the force that is expressed through a vector field. So let's take a quick note of that idea before we see how we can make that work. So again, we have a vector field, V. Let's just say that is defined on R to the N to R to the N. It's the same for, basically the same for more restricted domains, but for the sake of an easier treatment, we'll restrict ourselves to R to the N for a minute. So that represents a force field. Like, for example, gravitation. Or also an electric field, magnetic field, whatever you want. Maybe winds, etc. And then you have a curve, and that curve describes a path, a motion through that field. So let's say we have a curve gamma defined on some interval alpha beta mapping to R to the N. And that describes a motion through the field. V, under the influence of that force. So for example, that could be the movement of an airplane through winds, the movement of a charged particle through an electric or magnetic field, the movement of a person through the gravitational field of the Earth, or the movement of a satellite around the Earth. And what we'd like to do is we'd like to compute the work, the amount of energy that is necessary for that movement. Now, how do we do that? Now, as usual, what we do is we take this curve. Let's say we have a curve that moves like this, so that's the path, it's our gamma. Then we also have the vector field, and let's just say that's a very uniform, it's a constant vector field. Let's just say it looks like this. Right, so that's our vector field V. And now let's say we are at a certain point in that vector field. For example, let's take this point here. Then at this point, the direction of movement along our curve is precisely the tangent vector. And that also tells us the speed of movement, of course. So that's our local movement. And we want to know the amount of force that we experience at that point in time. So what we have to do is we have to consider the vector of the vector field that attacks at that point, and we have to project that vector onto our direction of movement. So here is the right angle, and then the force that we actually experience is the length of this projection here. Right? So this is the amount of force experienced at this point. So the amount of force that attacks in the direction of movement. Okay, in contrast to that, let's consider some other point to see how that changes. So for example, let's say we are at this point here, right? Then our direction of movement is this. The force that attacks at that point is precisely this here. And the force that we actually experience is again given by the projection of this blue vector onto our direction of movement. So the force that we experience is this here. That's the amount of force that we actually experience here. Okay, so that is a lot smaller because at that point the vector field and our direction of movement are almost perpendicular. Whereas in this point here, we almost move in the same direction as the vector field. And if we would move against the direction of the vector field, then of course we would also experience an attack of that force, but with a different sign. So what do we have to do here? We are interested in that red length, and the length of that is the effective strength of a force that we experience at that point during our motion along the curve. So the length of the red line is equal to the length of the projection of the vector field onto our current speed vector, onto our direction of motion. So that is the projection of our vector field V at a certain point on the curve, let's say V of x, onto our direction of movement And that direction of movement is given by the vector gamma dot of t, where gamma of t is exactly x. So we need to have the same point, of course. So we need to choose the point in time where the curve exactly reaches that point x. And we're interested in that length here, because that is the effective strength of the force at point x that is experienced moving along curve gamma, again at point x. So it's a local effect of that force. And if you want to know the global effect, so the energy that we have to spend for our motion, then we have to integrate the local effect along the curve. So what we have to do is integrate the projection of our vector field v at the point gamma of t. We project onto gamma dot of t, onto the local direction of motion. And we do this along the curve gamma. Okay, so let's compute that. We first need to find out what that projection actually is. So what you know is the projection. We're only interested in the length of that projection, not the vector itself. So that projection of the vector field onto the local direction of motion, well, we need to use gamma dot of t. And for the projection, you will remember that we always need to normalize the vector that we project onto. So we need to normalize gamma dot of t here. Right, so that is the effective force that we experience. That is the force effective at time t, or at the point corresponding to time t. And of course, this projection also includes the sign. And that is important because it is important if we work in the direction of the force or against the direction of the force. So the energy that we need is then expressed by the integral over that force that is effective at a certain point t along the curve gamma. So we're going to compute a curve integral here. And you know how to do that, of course, but let's first substitute what we know already. So that force, that effective force, is given by the integral over the scalar product of v of gamma of t with our direction of movement, which is again gamma dot of t divided by gamma of t. And we have to integrate that along the curve gamma ds. So let's use our formula for that. That curve integral, that can be evaluated by integrating from the starting time to the end time. So we integrate over the time from alpha to beta, because gamma is defined on the interval alpha to beta. And again, we integrate this scalar product expression here. So V of gamma of t, scalar product with, let's just say we have gamma dot of t in the scalar product, and we're taking out the scalar, this 1 over norm of gamma dot. By the way, there's a dot missing here. Okay, we're taking this out. And then for the integration along the curve, you remember what we have to do is we have to multiply the actual function. This is the function that we integrate. We have to multiply this with the norm of the derivative of the curve. So with norm of gamma dot. And we integrate over t, the time. And you hopefully notice that this expression here cancels out nicely. So what we are left with is actually the integral from alpha to beta over this scalar product here, V of gamma of t, with gamma dot of t dt. So this is what happens when we integrate along a vector field. And that is why we define the line integral of a vector field along a curve in just this way. So that's the definition. So let's say we have a vector field. So let V d to Rn be a vector field on a connected set d subset of R to the n. And let gamma interval alpha beta 2 d be a curve contained in D. Then the so-called line integral of V along gamma denoted by, so the notation for that is the same as the line integrals over scalar fields. You just write integral of gamma V ds. You again use that ds. Is defined as, so that integral VDS is defined as the integral from alpha to beta of the scalar product of the vector field at gamma of t with gamma dot of t dt. So that is how you define line integrals over vector fields, or extend the definition of line integrals over scalar fields to vector fields.